Congratulations on completing the first task and on drawing a graph showing the walker's position as a function of time. As you will no doubt have seen, the graph you should have drawn will look something like the graph shown on this slide. The walker progresses forward with each step he takes, and thus his position is a linear function of the time that has elapsed since he started walking. This is all well and good, but there is no element of randomness in the walker's progress, which, given that this module is on probability theory, is obviously not ideal. For this next task, you are thus going to introduce this random element. The walker will now be allowed to move both forwards and backwards. Furthermore, the direction he will move on each time step will be chosen randomly. In particular, if the walker is 5 meters from the origin, he will have a probability p of moving forward to 6 meters from the origin and a probability 1 minus p of moving backwards to 4 meters from the origin. His next move will also be random, so if his first move was forward, the probability that he will be 7 meters from the origin after 2 steps will be p once more, and his probability of being back at the origin, or 5 meters from the origin, will be 1 minus p. Notice that the two probabilities that I've just given are conditional probabilities. He has a probability p of being 7 meters from the origin only if his first move was forward. If his first move was backwards, then the event that has a probability p on the second step is his return to the start point 5 meters from the origin. Similarly, the event that has probability 1 minus p in the case of a first move that is towards the origin is arriving 3 meters from the origin. We can obviously fill in the missing spaces in the transition graph as shown here. Furthermore, we can imagine this transition graph extending out in both directions to plus and minus infinity. For each node in the graph, we then have a probability p that we will move forward on the next step and a probability 1 minus p that we will move backwards. We can thus write the following Python code to generate our position on the next step. In this code, the variable x is the position at the current time. As you can see, this code is generating a Bernoulli random variable and making a decision as to whether to move the walker forwards or backwards based on the value this random variable takes. To complete this next task, you will need to write code like that shown here. Furthermore, you will need to use a loop in order to ensure that your code is executed multiple times. You will then plot the position of the walker as a function of time and will get a graph that should look something like this. Unlike in the first exercise, however, because random numbers are generated within this algorithm, you will get a different result every time the code is run. I think that should be enough information to get you started, and I hope you are thus reasonably clear on what you have to do. Good luck.